Well, pre-calculus classes, good morning, good afternoon, or good evening. We will actually get started into what is our final chapter of first semester here with chapter 3. Again, probably a fair amount of review material in it from what you guys saw second semester algebra 2. And we're going to look at exponential functions, and then that will certainly move into logarithms later on in this unit as well. So we will talk about exponential functions, some of the qualities of their graphs, even though that's not a true parent function that we've talked about. You could even argue it is an additional parent function that we're going to look at. So an exponential function is of the form f of x equals b to the x. The base has to be greater than 0. It also can't be 1. If you took 1 to a power, you would just get a horizontal line. And then the exponent does have to be a real number. So if you have a graph or base that is greater than 1. And what I'm going to do is, certainly kind of just quickly sketch and use a few ordered pairs here as well. So if we have something like y equals 2 to the x, well, and I'm even going to start down here at the bottom. 2 squared is 4. 2 to the first is 2. 2 to the 0 is 1. Well, if you remember from earlier in the year, when you have these negative exponents, well, 2 to the negative 1 is a half. 2 to the, because that is 1 over 2 to the first. So if you have 2 to the negative second, that is 1 over 2 squared, or 1/4. So what I am now going to do, 2, 4, 1, 2, 0, 1, and then these 2 points get close to, but never cross, the axis. All right, so domain of an exponential function. I can keep plugging in bigger and bigger numbers for my power, or smaller and smaller numbers, so it's negative to positive infinity. As far as our range, well, exponential graphs have a horizontal asymptote. If it's just the parent function form, they never cross the x-axis. So the range is 0 to positive infinity. And then y-intercept, where it crosses the y-axis, 0, 1. It passes through, what this is referring to is the y-axis. When we get into logarithms as well, you'll see why we refer to that. It is an increasing graph from left to right, which means we also say it's exponential growth. Horizontal asymptote, as I said, it is the x-axis, so that makes it y equals 0. There is no vertical asymptote. And then it is what we call a continuous graph. If you think back, some of what we looked at in chapter 2, those rational functions, those were non-continuous graphs. Now, if you have an example where the base is between 0 and 1, well, I'm going to quickly sketch that one as well, or give you an example, and we'll use y equals 1/2 to the x. Well, again, what we'll do here, I kind of like actually starting with these. Well, if you square a half, basically all you've to do is square each number. 1 squared is 1, 2 squared is 4, so 1/4. 1/2 to the first, probably goes without saying it's a half, and then 1/2 to the 0 is 1. Now, if you take a fraction to a negative power, that's going to flip the whole thing. So 1/2 to the negative 1 is 2. if we do the same thing, 1/2 to the negative second will be, flip the whole fraction, 2 squared is 4. So there's negative 2, 4, negative 1, 2, 0, 1. And much like what we just did, this graph also does not cross the axis. Once again, I can plug in bigger and bigger, smaller and smaller values for the exponents, so the domain is just negative to positive infinity. The range, again, doesn't cross over the axis, so 0 to infinity. Y-intercept is still 0, 1, still passes through the y-axis, just like the first one. It is from left to right a decreasing graph, which is also known as exponential decay. Horizontal asymptote is still y equals 0. There is no vertical asymptote. And again, it is a continuous graph. Usually a graph that's not continuous is one that has a vertical asymptote, but that's not always the case. So that gives you some real basics to the graphs. Transformations. If you have f of negative x, meaning you have b to the negative x, if the exponent is negative, that is going to reflect over the y-axis. If you have f of x plus or minus some value, where you take b to the x plus or minus c, these are your horizontal shifts. The opposite of f of x, so if you have negative b to the x, that's going to be a reflection over the x-axis. If we have f of x plus or minus some value, biggest difference with this one and then this one up here is here we were adding or subtracting a value to the exponent. Now you're just adding or subtracting a constant to the function. Those are the vertical shifts. If you multiply a value by the function, so f of x equals some constant c times b to the x, that is going to be a vertical stretch or certainly shrink. And then if you multiply that value within the exponent, that's going to be a horizontal stretch or shrink. All right, so again, certainly you'll see some of those as you work through Chapter 3. The next thing, the natural base, E. I know when you guys look at compound interest, that's where we introduce this idea of E. We'll talk a little more about it, but it is roughly 2.718281828. It is an irrational number. I know it kind of looks like it starts with a repeating component here, but that is not the case. And, you know, you can certainly graph it to find the e to the x. Second ln is where e to the x is, and then just enter in the x. When you graph it, you can see it looks a lot like the exponential growth problem we just did, or graph we just looked at. And then as far as, you know, using e, if I go back to just calculations, again, to do like e to the negative 2, just press second and then your natural log button, e to the negative 2, it's like 0.135 to the negative first, 0.368, since it does say. That's the one thing you do want to watch, is make sure you do round appropriately. E to the first, well, 2.718 matches what's up there. E is kind of like pi. You know, that's the most common irrational number that you've used. You know, if someone says what's pi, you're going to say, oh, it's 3.14. Someone asks you what's E, probably more commonly you'll say it's 2.718. Now, that one's not as commonly known. We don't use it near as much as pi. And then E to the second, 7.389. So, as much as anything, these ones we just wanted to kind of let you see where that function is on your calculator. You know, as I was saying, where E has its derivation is with interest. Well, there are two interest formulas. One of them is the compound interest formula, A equals P times 1 plus R over N to the NT power. A equals total amount after T years, or the final amount. P is the principal or initial amount. T is your time in years. R is the annual interest rate as a decimal, which we'll talk more about that. And then N is the number of compounding periods per year, meaning how often do you get paid, or, depending on the possibility, do you pay interest? Now, compounded continuously. A equals, this is the PERT formula. And we'll talk about kind of where this formula comes from as we look at some examples. Again, A is your final amount. P is your principal or initial amount. T is the time, and then R is the rate. Obviously, it's a lot simpler than that one up there. And again, we'll talk about why that is as we look at a couple of examples. But these are the two formulas we use for interest. So, determine the balance at the end of 20 years if $1,500 is invested at 6.5% interest. And we're going to start out compounded quarterly. So, we're going to use, because it is quarterly, the compound interest formula. A equals your principal, 1,500, 1 plus now. Here is one of the big keys with this formula. As you see, it says interest rate as a decimal. 6.5% is not 6.5 that we plug in here. You do have to move the decimal 2 places, and it's 0.065. So I'm sure somewhere along the way you guys did that. And then if it's compounded quarterly, that means you get 4 interest payments in a year. And then 4 times 20 years. Now, one of the things that I always recommend here, before you enter this into your calculator, I actually like entering that in as just a single power. And you end up with $5,446.73. Because we're talking about money, we do want to round this out to the nearest cent. If you had left this as 6.5, you're going to end up probably with like an amount in the, maybe as big as like the billions, which would it be nice if $1,500 grew to billions? Yes, it's not practical that it will. So with these formulas, you can always kind of see, hey, does what I ended up with, does that make sense? Now, compounded monthly. You know, some of your investments are compounded monthly. I know if you get a what's called a CD, that is something that's going to compound monthly. You know, other things as well. A lot of your retirement accounts, like as you get older, you know, if you've heard your parents talk about their 401k, those are things that also compound monthly. So, only thing that's going to really change here is N. That's now 12. Because if your interest is compounded monthly, you get 12 times a month, 12 times 20, as your power is 240. And so again, now when we enter this in, you end up with a little bit more. $5,484.67. The more often you are paid interest, you know, the little bit more quickly your money will grow. Now, there is a limit to just how much you can earn, and that comes in with compounded continuously. That's where E is derived from. You know, E is the limit for just how much money you can gain if you are compounding any quantity over time. So, if you see that word continuously, that's where we now shift to the PERT formula. You know, as far as what changes, well, the principal is still 1,500. The E is E, and then the rate 0.065 times 20. And for this, I don't actually worry about multiplying those out. And the reason is your calculator usually opens up a parenthesis. Some of you, the newer models of calculators do that, and so then it's not as important that you multiply those first. But here you can see, if you are investing $1,500 at 6.5% for 20 years, the absolute maximum that you could have is $5,503.95. That's what the continuous compounding formula shows us. All right, so one last example here. The number of fruit flies in an experimental population after T hours is given by Q of T equals 20e to the 0.03t, where T is greater than or equal to 0. So, what is the initial population? Well, there's actually two ways you could do this. The initial population is at time 0 when they're starting that experiment. If you plug 0 in, this is 1. Or, if there is a value in front of your exponential base, that's going to be your initial population. So it's kind of like that vertical stretch amount represents that. But again, if you plug 0 in, that becomes 1. So there are 20 flies. Now, here's where you have to be careful with this next one. How large is the population after 3 days? If you read through up here, experimental population after T hours is this. Well, if you just plug 3 in here, you're going to actually see how many flies are there after 3 hours. So to figure out after 3 days, we actually have to take 3 times 24, which is 72, and then plug that in. And here's the other thing that we're going to now talk about is after 3 days, when you are talking about any sort of animal or any sort of, human population, don't round off to the nearest hundredth. If you're talking about money, absolutely. But when you're talking about an actual population, we do want to use whole number values. So that at least gets us started into exponential growth and decay in Chapter 3.